Hello, and welcome back to Learning with Lee. I understand that the previous episode was titled so as to imply that this episode we would be continuing our discussion of variables. However, at the present time, I do not feel that we have a sufficient background in other aspects of computer science in order to properly give that discussion of variables its full and proper coverage. What we're going to be looking at today are what are known as expressions. Expressions are what any one of these lines in here happen to be, whether it be this which outputs a character, this return statement, and statement is just another word for expression in programming parlance. And an expression consists of multiple operations which themselves consist of multiple operators and operands. And the terms operation, operators, and operands come from the math world. And the reason for that is that a lot of these things might be something like 20,000 plus 10,000. That happens to be one operation consisting of two operands and one operator. Now, the fact that it also has this equal sign here means that there's another operation taking place, and that's the assignment operation. And that's the same thing we've been doing with all of these, which really just is to say, I have some data on the right-hand side of the assignment operation. I want to store it in the memory referred to by the left-hand side of the operation. So, 0 gets stored in some amount of memory described by short s. Technically, there's a hidden operation here, and that is the construction of the variable s as a short, and creating that memory and allocating all of that. So that's a bit of a hidden operation there, but really the major one is the assignment operation of s equals 0. As you might have guessed from the earlier use of this addition operation here, there happens to be the full suite of mathematical operators: adding, subtracting, dividing, multiplying. There is one sort of weird caveat that can occur. Let's say that I did 20,000 plus I. The question then is what type is 20,000 plus I? You might be thinking to yourself, well, it's a long. But the thing is that because of the way in which computers handle these expressions, because it hasn't yet tried to store it in a long, it's not going to convert this into a long unless it has to. It's going to use whatever its default data type is, which for something like 20,000 is actually going to be an int. And because, in this case here, it's basically going, okay, I'm adding in two ints, and then it's like, okay, I need to store an int in a long. And this happens to be known as type conversion. And more specifically, this is implicit type conversion because you're letting the computer decide it for you. You can explicitly do a conversion by doing this. In case I wanted to convert this into a long before I store it in the long, I would do something like this, in which these parentheses surrounding a data type, whether it be a primitive data type such as these here, or a complex data type such as string, any one of those you could put here and it will convert whatever's over here into that data type. Unless the two types cannot be converted from one to another, in which case it will give you an error either now or when you try to compile or run your program. Now, these parentheses on the right-hand side aren't actually necessary here. Well, I'll get into how they are used, but what this does is it goes, in case let's say I did this instead, it would convert 20,000 into a long, add I to that 20,000. Because 20,000 now happens to be a long, I would get implicitly converted to a long, since long has a larger memory usage. Then what would happen is that it would get stored in L with no additional conversions needed. Alternatively, I can go, okay, I have 20,000 plus I, and this happens to be, I want this all to take place, and then I want it converted to a long. And what these parentheses here act as is they are precedence operators, and they basically say that whatever is within those takes place before any operations involving that value and data that might be on the outside. So let's say that I had 2 times that value. Normally, without these operators here, you would get 40,000 plus I. In this case here, though, you get 20,000 plus I, and then you multiply by 2. Those examples don't really show you why I would want to use type conversion, but let's say that I wanted to do long L equaling 2 times 20,000 divided by 3. Now, the fact of the matter is that for this, I don't necessarily need precedence because of the fact that regardless of whether I do the 2 times the 20,000 first or 20,000 divided by 3 first, that order of operations doesn't really matter. Now, let's say, though, that here's a problem, though. If I do 20,000 divided by 3, here, I'll show you what that results in real quick, and you'll see why there's a problem here. Build it, run it. Notice how it doesn't have anything after it, and notice how it does this. And that's because of the fact we're converting it to a long here. But even if I convert this to a float, you might think, okay, sure, no problem. Now it's going to have the 0.66 repeating afterwards. Except it's not going to, because neither of these is a float. As I was saying earlier, it focuses on this operation first. It doesn't focus on what type it'll end up being. It focuses on what type these two are in the operation. So we currently have one that happens to be effectively an int, and another one that effectively happens to be an int. And when you divide an int by an int, it truncates or removes anything from this decimal place onwards. So if I, let's say, though, wanted to go, okay, let's say that I do 3.0. That's similar to how I did it here. I can do that. I can run it. That's great. Now let's say that this, though, is a long, and I go, okay, this part here, just using common sense, is going to get truncated. That much I know. But let's say that instead I had 20,000 plus 50. There's that. And this happens to be divided by I, and I is 3. But in this case here, I need to convert one of these into a float, because otherwise I'm going to lose some information potentially. Or if I do something like 20,000 divided by I, and then I multiply it by 50. Because in this case here, that stuff that would be down here would end up not multiplying, and we would end up being significantly short of the value we would expect. So what I have to do here is convert I into either a float or a double, depending on how precise I want that information to be. Do that, build it, run it. Whereas if I don't have I as a double there, and then I build it and run it, notice how we lost 33 in terms of that information. So that's the main reason why you do things like type conversions, is to prevent lost information. The other reason to do type conversion is let's say that I want to find out what int represents character C. And not to get too much into how characters are stored in memory, but really all you need to know is that they are a number between either 0 and 127 or 0 and 255, depending on whether you're using ANSI ASCII, which is 7 bits, or 8-bit ASCII. Technically, they can be larger if they're Unicode, but we're not going to get into the differences between Unicode and ASCII quite yet, or how characters are stored in full detail. But all you need to know is that there is actually an integer that corresponds to B. So I could do outputting C, but let's say I want to output it as an int to find out what that number is. C, and then B is 66. Alternatively, I could do what is C minus A. In this case here, I'm going with lowercase a, because you could probably guess that in case, since this is B and that's capital A, then it happens to only be one off. But in this case here, are the lowercases stored in ASCII before or after the capital letters? And this will let you know. And as you can see right here, that means that these get stored afterwards. And to clarify why that is, that's because A has to be larger than C to wind up with a negative number. And the only way that that would be is in case A happens to be further down in this table, so as its index into character A is later on than its index into character B. So you can do those type conversions. You could also do something such as C minus I. And then if I do that, run it, gives me this. However, let's say I want to find out what character is at that location. Have to use both the type conversion and precedence operators in addition to the subtraction operator in order to do this. And as it turns out, it's a question mark. And you could do this for, like, let's say I want it to be whatever's 40 below. Build it, run it, and then it winds up with this, which is saying that it can't actually display that character. Because in case I go like 41, then it's going to give the same thing. And that just is how your system tells you that you're trying to display something that really shouldn't be displayed. But this is just the normal question mark, and if I say went -1, it would give me A. So that happens to be another use for type conversions, is in case you want something like the output to be in a specific form. But in general, it's used so as that you can retain data when converting, well, either when doing math, when converting between types, as well as making certain that things are explicitly how you want them to be and not relying on the computer to be intelligent enough to actually do things correctly. Another type of operator that we haven't particularly covered, though we have indirectly, is the ability to combine a mathematical operator with a storage or assignment operator. And this is a fairly common thing in computer science and programming, and that is that let's say that f already has some value, and then I want to update its value by dividing it by d. Normally what I would do is I would do f divided by d, like this. So as that it's like, okay, I'm assigning f the value of itself divided by d. However, in order to simplify that, you can just go, okay, whatever mathematical operator you want, in this case division, followed by the equal sign, and it will end up updating f with f divided by d in this case. And just to briefly show that that does indeed work, build it, run it, and there you go. Having said all that, there is one common mathematical operator which does not exist in at least this programming language, as well as any that are derived off of C and C++, such as Java and C#. And that is the power operator. If I do something such as f equals d, and normally we do something like that to the 5, that's going to actually do something very different from what you expect it to do. It is not going to raise d to the 5th power, or effectively do d times d times d times d times d times d. It's not going to do that effectively. If I do this, it's going to do something completely different, and we're going to get into that in the future. You need to understand that there are things in libraries to allow you to do exponents and to do things to a certain power, but it is not a built-in operator of the programming language. And with that, we've covered the majority of the mathematical operators in C and C++. There technically is one that we haven't covered, but I feel that that one is uncommon enough that it deserves its own episode. And we'll either cover that one next time or what are known as the logical operators next time. And with that, thank you. I hope you all have a wonderful day.